This section of your reading lays out a problem-solving process for you, and they use the words understand, solve, and explain as a way to summarize and help you remember what you're supposed to do as you're solving problems. Now you'll notice, perhaps if you've read other math textbooks before, or if you have any experience with problem solving, that the process that they've mentioned should sound fairly similar to things you've heard before. And they may have named it slightly differently, but if you're thinking that this sounded really familiar, but you just maybe know a slightly different way to say this or to solve problems, there's a reason for that, and that is that in 1945, mathematician George Polya wrote a book called How to Solve It, and this was fairly influential. It's a bestseller. It's been in print ever since then, and many textbooks use some variation of his method. So his varies slightly. He has 4 steps. The first is understanding the problem, and then he breaks the solving step up into 2. One is to devise some sort of a solving strategy, and then the second part of that would be carrying that strategy out. And then instead of the last step being explain, he says to look back, which would involve some of those same steps to check your answer and to see if it makes sense. So again, use whatever terminology you like, but it is a good idea to have some sort of a problem-solving process in the back of your mind as you go through problems like this. And if this helps you to remember it, USE or use, then that's a nice tool as well. All right, I hope you picked up from this section of the reading there are really 2 main goals in using units. One is it is its own goal, which is to convert units. So if you need to convert from metric to English, or just from something like feet to inches, then that might be the goal itself. A second goal is to use units as a tool for problem solving. So this gives you a chance to practice that problem solving process, but also do something that is fairly practical and useful in and of itself. Right? So when in doubt for a problem, if you do see that there are units involved, you can sort of just follow those units, even without really having a completely clear idea of what the problem means or what you're supposed to do. And you'll often get either the answer or close to the answer just by kind of considering those units. Right? So I want to just encourage you to think about understanding a problem in perhaps a slightly different way. With math problems, I try not to think of understanding as meaning I know what the entire map looks like, I know how I'm going to get from point A to point B, and I feel really confident about each and every step. Sometimes understanding just means knowing what the end destination is, and maybe just knowing the first step, or having an idea of something that you might try. Right? So that's at least enough to get you started. And this really is not a linear process. Sometimes you kind of need to go back and forth between these various steps. You may think you understand a problem, you start solving it, and you realize you didn't really understand it, so you go back to that first step. Right? Or perhaps you get all the way to explaining the problem, and then you notice that something doesn't sound right or doesn't make sense, and you've got to start all over again. Right? So this is really more of a circular process. It's not linear. Okay, let's try a few example problems. So we will work with units and conversions, and in the process, this is a good chance to practice some of those problem-solving skills and implement that type of a framework. All right, I don't know if you are a white lights person or colored lights. Personally, I'm a white lights person, but I thought we would do some conversion with Christmas lights. So your reading mentioned kilowatt hours as a common electricity unit, right? So I did a little bit of research. Christmas lights, a typical string of maybe around 100 bulbs or so, the incandescent ones, not the LEDs, uses 40 watts of energy, electricity. All right, so let's see if we can convert that into kilowatt hours. And of course, we do need a time. So let's say maybe in December you decide that you're going to have your lights come on at 5 p.m. and you'll put them on a timer so that they go off at midnight. All right, so you're planning to use these for 7 hours a night for the entire month of December, and we're curious how many kilowatt hours that would be. All right, so we have usually two things here, and this is a good place to start with understanding the problem. All right, think about what's known. So we have that. We know 40 watts, and we know some sort of a time. Okay, so that's 7 hours. And then what is it that we're trying to find? So we want to find kilowatt hours, and that's unknown. Okay, so we'll start with what's known and work towards that kilowatt hours. All right, so if I were to write out what is known as more of a phrase, what I know is that I'm planning to use 40 watts of electricity for a time of 7 hours per day. Okay, so we have a couple keywords in here. We have of and per, and that gives us an immediate place to start here. All right, so this is 40 watts, right, for a time of 7 hours, so that means times. All right, and then per day, so that's divided by days. Okay, so I'm going to write this as a fraction per day. Okay, but you could also use your division sign if you like. Okay, so if we look ahead at what we need, we're trying to find kilowatt hours, and notice the hyphen, which does mean multiplication. Right, so this is looking good. I have watts, I have multiplication, and I have hours. So really the only thing we need to worry about here is that we have watts instead of kilowatts. Right, so there's a bit of unit conversion we can do there. And if you look this up or know this, 1 kilowatt is 1,000 watts. So let me write that off to the side. All right, 1 kilowatt is the same as or equals 1,000 watts. All right, so as soon as you have two things like that that are equal, we can use that as a conversion factor. So you could write this as 1 kilowatt divided by 1,000 watts. Okay, or you could write this as 1,000 watts divided by 1 kilowatt. Okay, and either one is equivalent to 1. Right, since these two quantities are the same thing, we have a fraction that's just 1. So that means I can multiply this 40 watts times 7 hours per day, okay, by one of those two fractions, right? And what I want to do is cancel out the watts and change that to kilowatts. So we would need, this initial watts is in the numerator of a fraction. You can put that over 1 if that's helpful. Right? So that means that when I multiply, I want to have watts in the denominator so that that cancels out. Right? And I want kilowatts in the numerator. And then that tells me where the number should go. So it's 1 kilowatt per 1,000 watts. Okay, so then I like to do the units first just to make sure I've set this up correctly, and then I go back and do the numbers separately. So what I would probably do here is, let's cancel these watts. So this initial watts and the last watts will cancel. Right? And then I want to just check the units that are left. So I have in the numerator, I have hours times kilowatts. So that is kilowatt hours. And then in the denominator, I have days. So this is per day. All right? And then we can do the numbers, which are going to be 40 times 7, which is 280. Okay, divided by 1,000. And then make sure you put in the units. So this is kilowatt hours. I don't know if KW actually abbreviates kilowatt, but I'm just using that to save space. Okay, and then in the denominator, this is, we've got days still. Okay, so then now we can divide 280 by 1,000, and we can do that by just moving the decimal in 280 3 places to the left. So this is going to equal 0.280 or 28 kilowatt hours per day. Okay, so that's how much electricity this string of light bulbs uses per day if I'm going to run it for 7 hours. But typically, I mean, you'd have a certain season that you run the Christmas lights. So let's say you want to calculate how much electricity is used for the entire month of December. So that's 0.28 kilowatt hours per day. And then what I want to know is how much per month. Right? So we need to change days to months, and we can do that by multiplying again. Right? And I want the days to cancel. It's in the denominator now. So I'm going to multiply by a conversion factor with days in the numerator and then months in the denominator. And of course this varies, but for December we've got 31 days in 1 month. Right? And let's do the units first again. So days cancels, and now we're left with kilowatt hours per month. Okay, and then 0.28 times 31 is about 8.68. Okay, so there's the answer. If we're looking for the electricity usage for December, 8.68 kilowatts per hour for the month, and that's just for one string of Christmas lights. Okay, and then, well, what can you do with that? We could go even further. If you knew how much electricity cost, then you could figure that out, the cost for a string of lights, and then you could multiply by however many strings of lights you're using. Another type of conversion problem involves units raised to certain powers. So we might work with cubic inches, cubic feet, square miles, square yards, things like that. So typically, I don't usually memorize all of those conversion factors. I usually just know the ones for single units. So for example, if we needed to convert 3,500 cubic inches to cubic feet, I don't know that conversion factor off the top of my head, but I do know the one from regular inches to regular feet. Right? So here's how you would convert this using just that one conversion factor, right? Which is that 12 inches is 1 foot. Okay, so start out with the thing that you know, right? Which is 3,500 cubic inches. And then we need to convert to cubic feet, so that's the answer we want to end up with. Okay, so starting with the 3,500 cubic inches, right, that's inches cubed, or we can write that as inches times inches times inches. Okay, so writing it out like this makes it fairly clear what conversion factors you need to use. Right, so what I need to do is cancel inches 3 different times. Right, so I'm going to multiply this by feet per inches. Let me space that out. Okay, now doing that once is going to cancel one of the inches, but then that would leave me with inches squared times feet, which is a little bit weird. So we need to get rid of the other 2 inches as well. So I'm actually going to multiply by this feet to inches conversion factor 3 times. Squeeze this in. Okay, and then that takes care of the units, but I do need to fill in the correct numbers. So it is 12 inches per foot. All right, and then if you look at the units here, so we have 3 inches in the numerator that cancel with 3 inches in the denominator, and we're left with 3 feet in the numerator. Okay, so this will give us cubic feet as an answer. Okay, so that's what we want. And now that I know that this is set up correctly, I can go back and do the numbers. So I would need to do 3,500, right? And I'm multiplying it by, if you just see feet, okay, this is just 1 foot, so you're multiplying it by 1 3 times, and then you're dividing it by 12 3 times, or 12 times 12 times 12. All right, so that's 3,500 divided by 1,728. Okay, and then that's going to give about 2.003 feet cubed. And you can check that and round a bit differently to something that makes sense. All right, so it's about 2 cubic feet. And I think you could see how this would translate. So if we needed, square inches to square feet, you would only do this twice. And you could do the same thing even if it were not inches and feet, if it were square centimeters to square feet or something like that, then we would just repeat the conversion factor as many times as needed.